Hi everyone, it's Professor Sebastian. Welcome back to our statistics class notes. We're on page 107, the second page of our section 7.4 notes. From the previous sections, we do know the following facts. Our estimator p hat is an unbiased estimate of the population parameter p. Therefore, the population parameter p should be close to the sample statistic p hat. Okay, so we always assume that when we do a sample and the sample is done correctly, it's random and independent, it's large enough, and the population is big enough that it's an unbiased estimator. The standard error is estimated as the following. So the standard error estimate is the square root of p hat times 1 minus p hat divided by n. So we've plugged in p hat instead of p. The true standard error is if p were in there, but we don't know it when we're doing these kinds of things. So plugging in p hat, we get this, 0.0143. So because the sample size is large, the probability distribution of p hat is approximately normal and centered around the true population parameter p. In other words, it's normal, capital N, of p as the mean, comma, SE, standard error, as the standard deviation. Now we're estimating both, but that's okay because we're assuming p hat is close to p. There's about a 95% chance that p hat is within two standard errors of the population proportion p. That's using the empirical rule. Thus, we calculate two standard errors to get 2 times 0.0143, which is 0.0286. These are the standard error estimates. So we are 95% confident that the value of the true population proportion is within 2.86 percentage points, right? That's changing the standard error to a percentage, of 57.04%, changing p hat to a percentage. So if I subtract 2.86% from 57.04, that'll be the lower limit of my what's called confidence interval, which is 54.18%. And if I add the 2.86 percentage points, I get an upper limit of 59.90%. So the way we state these confidence intervals, we say the following. We are 95% confident that the population proportion, which in this case is the proportion of all American adults who support legalizing marijuana, is between 54.18% and 59.90%. That's called a confidence interval. Confidence intervals do a few things for us. They provide us with, one, a range of plausible values for a population parameter. That means values that we can expect to likely be true. That's a range, right? We have a range that's anywhere from 54.18% to 59.90%. We can never pinpoint anything specifically in there. We're just 95% confident that it's somewhere in that interval. Confidence level expresses our confidence level, which is this 95%, expresses our level of confidence that the interval contains the population parameter. Information, the confidence level actually, also tells us how often the estimation is successful. So when we say we're 95% confident, what that truly means is if we had done 100 different samples, so remember that sample was 2,003 different people, right? It's going back to the previous page when we started this example. So if we had done 100 different samples, all of 2003 size, which we don't do in practice, remember this is theoretical, the confidence level actually tells us that 95 of those 100 samples would contain the true population proportion. So what we're hoping is that we have one of those 95 correct confidence intervals. So it's important to understand that the confidence level measures the success rate of the method, not of any one particular interval. We're just hoping that we have one of those 95 intervals that has the true population parameter in it.